Go ahead, Mehmet.
Thank you, Dina. Good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. We are delighted to have Dr. Bruce Jakosky as our guest speaker this evening. Dr. Jakosky is a Senior Research Associate and Associate Director for Science in the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. Bruce has been involved with Mars for over 40 years. He led the Mars Atmosphere and Volatile Evolution MAVEN spacecraft mission for 18 years, from inception through 7 years of operation at Mars. He is very knowledgeable about Mars, obviously, a planet where our children or our grandchildren may go and visit to or live in the future. Bruce, please proceed with your presentation.
Thank you for that introduction, Mehmet. And I am going to come back to your comment about our children and grandchildren as we get into this, because I think that's an important point. What I want to do is talk tonight about the planet Mars as a whole and some topics that really play together, and that is the history of water, the behavior of water, the behavior of the climate, and the potential for life. And that's going to lead into a discussion of how we search for life and possible human missions to Mars, and maybe terraforming and colonies on Mars. One of the things that always strikes me as I give talks like this, or when I talk to people that I meet, not in the business, is that Mars is always in the public eye. Everybody is interested in it. Everybody has an interest. I picked a handful of images here just to show the breadth of Mars, from David Bowie in the upper left, a recent board game called Terraforming Mars that I understand is very popular. I can't quite bring myself to try to play it. It hits a little too close to home. That image in the lower right, if you recognize it and know what it is, it needs no explanation. And if you don't, there's just no way I could explain it easily. It relates to the Doctor Who TV show. The interest in Mars is, I think, driven a lot because not only is it our nearest planet, and not only does it show a lot of geology and atmosphere and seasons very reminiscent of what we see on Earth, but it has the potential for life. And in fact, one of the overarching questions for Mars is it habitable? Was it habitable in the past? And did Mars ever have life? The question of whether it had life is one that is central to our exploring Mars today. By the way, this is an image of the Allen Hills meteorite on the left. That little scale cube in the lower right is 1 centimeter across. This is a meteorite that almost 30 years ago now drummed up a lot of interest in whether there could be life on Mars. And that image on the right shows something that was interpreted by some as possible fossil evidence for life. This question of whether Mars is habitable and ever had life didn't, as an overarching question, it didn't just come out of the blue. It came as the result of 75 years, I'll say, of exploring Mars. And this exploration really started 100 years ago with telescopic observations. And then as we got into the spacecraft era, we had flybys, the first orbiters, the first landers on Mars, the first rovers. And the next to last image on the lower right is my favorite spacecraft, the MAVEN spacecraft. That one has been doing the most important job of exploring the upper atmosphere. And then most recently, a helicopter on Mars. With the spacecraft measurements and with ongoing Earth-based telescopic measurements, we've really come to the point of understanding that there could be life on Mars, or there could have been life on Mars. And we're trying to understand where it might be, what conditions life might exist in, and what actually is there. I want to start, though, with life on Earth, because if we're going to look for life on Mars, we have to know what life is. And I picked here a sampling of terrestrial organisms, everything from tiny microbes up through those ugly fish, that ugly fish in the top middle, and humans and apes. The most important thing to get from looking at this tremendous diversity of life on Earth, everything from single-celled up to very complex organisms, is that it really represents only one example of life. And by that, I mean that all life on Earth shares a common biochemistry. This is a schematic of part of a DNA molecule. We all share DNA that suggests a common origin. We use the same 24 amino acids. We use RNA to help transfer information. If we trace it back, all of life on Earth is genetically related to each other and really represents a single origin of life. This is very important as we try to extrapolate to what are the conditions under which life can exist elsewhere. We have only one example, and we're trying to generalize to conditions everywhere from this one example. The other important characteristic, by the way, my screen is blocked a little bit by the control bar. Are you seeing the words at the top of the screen?
We are.
Okay, great. I could try to move the control bar if I needed to, but I know what it says. So if you're seeing it, we're good. The second important thing about life on Earth is that we can look at life in extreme environments. We're used to looking at the life outside of our window. We see plants, animals, people that live at what we think are very clement conditions conducive to life. But what we find is that there are organisms on Earth that live in very extreme environments. The upper left, for example, is Grand Prismatic Spring at Yellowstone, which is essentially boiling water, admittedly at reduced temperatures because of the higher elevation. But all those colors represent organisms, and it's in a nice bullseye pattern because those organisms have sorted themselves by the temperature. The stuff at the outer edge lives in hot water, warm water, the stuff inside of that in hot water. The other example of life in a hot environment is in the lower right. Those are tube worms that live off of chemical energy from hot springs at mid-ocean spreading centers. That is, they live off the energy that comes out of water circulating through volcanic regions below the ocean. The one in the lower left is radiation-resistant bacteria that may have evolved to live in a very dry, desiccating environment. And in the upper right, life that lives at sub-freezing temperatures. When we look at the range of conditions in which life can exist, it's an incredibly broad range. And if we try to summarize it, it appears that life has a very simple set of environmental requirements to be able to exist. We need access to the biogenic elements, the elements that construct organisms: carbon, hydrogen, oxygen, nitrogen, and about 24 others. We need a diversity of elements in order to combine together in different and complex ways and begin to have functionality. We need a source of energy that can drive metabolism, that can bring the chemicals together and construct more complex molecules. That energy can be sunlight, it can be chemical energy derived ultimately from reactions, for example, between water and rock. And then we need liquid water. On Earth, liquid water is all around us. It may or may not be present elsewhere. We need it as a medium in which life exists, something through which nutrients can diffuse into an organism, waste products can diffuse out, and chemicals necessary to support life can dissolve or not, depending on the conditions. Okay, finally, let's go to Mars now. And what I want to do is walk through those requirements and see if they're met. Start with a little introduction about Mars, although I'm sure this group needs no introduction to the red planet. Mars is about half the size of the Earth. It's about 1.5 times as far from the sun as the Earth is, so it's colder. It has a much thinner atmosphere than the Earth. It's only about 0.5% as thick, and it's primarily carbon dioxide rather than the Earth's nitrogen and oxygen atmosphere. By the way, I hope everyone realizes that Earth is the one on the left, Mars is the one on the right. In the image of Earth, you see all of the ingredients necessary to support life. You see liquid water. In the land areas, in the top of the image, you see all, well, you can't quite see them, but you know that all of the elements necessary to support life are there in the dirt or in the atmosphere or in the water. And you see the energy supporting life in the form of sunlight, which we're seeing reflected off the planet, or in the form of chemical reactions between water and rock. What I want to do now is start looking in a little bit more detail at Mars. We often think that Mars today is not a place conducive to life. It's a cold, dry planet. Here are a couple of images from the one on the left from Viking, the other from Perseverance. These show a dry, desert-like planet with temperatures averaging about 50 degrees C below the freezing point of water. If you stand at the equator at noon at the middle of summer, the temperature will get up above zero, but it doesn't stay there very long. It's hard to imagine water persisting for very long, even if it were present. On Mars, the weather is driven to a great extent by the behavior of dust in the atmosphere. This is in contrast to the Earth, where the weather is driven a lot by water that evaporates from the oceans or from land areas. But we have dust driving the temperatures, driving the circulation of the atmosphere. Dust can be raised by dust devils. On the left, we're looking down on one. So it's a little bit hard to see, but that shadow is what's cast by a vertical dust devil. And then up to local and regional dust storms, and then occasional global dust storms that blanket the entire planet with dust. Now, there is water in the atmosphere, but it's not very much. It's enough to produce clouds like you see in the image on the left, but the graph on the right shows how little there really is. This is the amount of water in the atmosphere as a function of latitude and season for one Mars year. The units are precipitable micrometers. That is, if you took all the water as vapor in the atmosphere and precipitated it out onto the surface as a thin layer, how thick would it be? The most we ever see is 100 micrometers of water. That's 1/10 of a millimeter. That's not very much. These are very tiny amounts of water. And when it does condense as clouds, it almost certainly condenses as solid rather than as liquid like we see on Earth. There's water ice that is more widespread. In this image, you can see that bright white polar cap up at the top of the image. That's the residual North Polar Cap. It's primarily water ice or water ice and dust mixed together. And when we look at it closer, it's got some interesting geology in it. We see these dark lanes that really we don't understand why they form that nice spiral pattern. There's a lot of speculation and not a lot of data. If we look even closer up, though, we see that the water ice appears to have been deposited in layers, alternating layers of water ice and dust, or of dust and ice mixed in different proportion. And you can see through these wavy features that deposition is not necessarily uniform. That rhythmic deposition suggests a changing climate. And that's not surprising because based on theoretical analysis, we understand that the polar axis of Mars increases and decreases its tilt. And that can drive the climate on Mars much as the same process drives the climate on Earth. And then when we look closer up, we see features that are tens of meters across. These are actually pits. To my eye here today, they look like raised bumps, but they're pits being carved out by sunlight in the ice. In addition, we've recently discovered massive non-polar deposits of ice, in this case, colored with false color as blue because people like blue to represent water. I'm using the term massive in the geological sense. That doesn't mean humongous. It just means a thick mass of solid material. This stuff is within a few tens of meters of the surface and is a layer hundreds of meters thick. How did it get there? And is it stable there? These are important questions that relate to the climate, and we don't know the answers. Now, there is the possibility of liquid water occasionally. We see gullies. Let me take a second here and bring up my laser pointer so I can point to things. I hope you can see my laser pointer here. Nice red color. On the left, there are these things that are very reminiscent of gullies on the Earth. This is on a steep slope going downhill where material has been carved out here and deposited in this apron at the bottom. There's an ongoing debate as to whether this would have been carved by liquid water or by some dry avalanche process, and I'm not prepared to give an answer. The middle image has what's been called recurring slope lineae, these features that come and go and extend out through the season. These look for all the world like they involve water. But again, we don't have definite proof. And this one on the right is the most intriguing in some ways. We're looking at a strut on the Phoenix lander, which landed at high northern latitudes, and what looks like droplets of water on top of it. It doesn't show up clearly in this image, but other images show that it really is droplets of water. They discovered a chemical called perchlorates, ClO4, and these perchlorates actually can suck water vapor out of the atmosphere and turn it into stable liquid. These are now thought to be widespread over Mars, at least in trace amounts. So it raises the possibility of widespread trace amounts of liquid water. Now, even if liquid water isn't abundant today or doesn't even occur today, we have evidence that it has occurred throughout time. We see features like this, these dendritic networks of valleys where you have smaller valleys coalescing into bigger ones and coalescing into still bigger ones. These look for all the world like they were formed by the runoff of rainfall, precipitation. And that's actually the best interpretation today. We see features like this that are more reminiscent of, actually, before I go on, let me say that these valley networks are maybe 10 to tens of meters across to maybe a kilometer across. They're very small scale features. At the other extreme, we have these features that look like large scale flood features that appear to have been carved by water. And you can see that water flowed in from left to right here, where it hit this impact crater, it flowed around it and created a streamline shaped island. And I want to draw your attention to that scale bar in the upper left, 100 kilometers. What that means is this thing is 150 kilometers or 200 kilometers across. and it had water flowing through it at one time. That is equivalent to the Mississippi River in flood stage. And we're seeing just evidence for a lot of water here. This water doesn't, unlike the Mississippi, this water doesn't appear to have come from runoff of snowmelt or rainfall, but it appears to have come full born out of the subsurface. Here's one channel where off on the left, you see the well-defined channel with striation marks that are similar to what you would expect to see from water. And if you go upstream, you find this jumbled chaotic region here. And it looks like the water just sort of blurped up from under the surface and then flowed out over the surface. You can ask whether water is the best explanation for these features. There have been a number of explanations put forward over the years, including wind or being carved by volcanic lava, although lava tends to build up things rather than carve them down. I've even heard a suggestion of oil created photochemically in the atmosphere running across the surface and carving these. And I'm going to use what I think is a very technical geological argument as to why these must have been carved by water. And this is the most technical thing I'm going to say tonight. But we think that these were carved by water because they look like they were carved by water. I'm not being totally flip because that's how planetary geology works. You look for features and understand through analogies with similar features on the Earth what happened, how they could have been formed, and water is really the only viable explanation for these. We see other water-related features like this impact crater, which once held a lake. This is Gale Crater, and the Curiosity rover landed inside this ellipse. Gale Crater was an impact crater. You can see where water flowed out of the crater and elsewhere where it flowed in. These large flat areas in the bottom are sediments that were deposited in a lake there. The Opportunity rover observed this hillside on the inside of a different impact crater, and it shows what appear to be sediment deposits layered here as if they formed in a standing body of water and then jumbled up here. These give the appearance of having been formed in liquid water. And finally, we see a lot of minerals mapped out over the planet that require liquid water in order to form. Every dot you see on this image is the location of a mineral that only forms in the presence of liquid water. So we have a lot of evidence that there's been liquid water through time. This really lets us meet that first criterion about the most important criterion about whether life could exist, and that's the presence of liquid water. When were these features formed? This is a horrible plot, but I put it in here because it shows the timing of some of the features. This is a time scale from planetary formation 4.5 billion years ago up to about 2.5 billion years after formation. And these ugly features here show when different features form. The wider the bar, the more activity there was. So it shows impact cratering, the valley networks I mentioned, the flood channels, volcanism, and so on. And I've circled here the ones that are related to the presence of water. The minerals that form only in the presence of water, very high erosion rates in the earliest epoch, the valley networks. All of these are ancient features on Mars, and they're extremely rare after about 3 billion years ago. That is, within the last 3 billion years, they're extremely rare. We can also look at the features that produce water. And I'm going to talk about both of these in just a moment. Volcanism, for example, has been an important source of water. As the lava erupts to the surface on Mars, much as when it erupts to the surface on the Earth, it releases a lot of water into the atmosphere. This water has been a significant component of the total water inventory on Mars through time. And I want to now relate the tectonic behavior of Mars to water. And this is going to take me a moment. This actually is the, no kidding, the only technical part of the discussion. First, let me draw your attention to that red oval at the left. This is Olympus Mons, the largest volcano. These three large groupings are the Tharsis volcanoes, and this whole area is an 8-kilometer high bulge. Now, that mass of stuff sitting on the surface cracked the surface, and all those red marks are cracks, extensional faults that radiate out from this bulge. It's exactly what you expect to form when you put a heavy mass down on the surface. Now, this one here is of particular interest because it turns out that it coincides, that extensional faulting coincides with the large the large canyon system, Valles Marineris, shown in this image. We're looking at a canyon that is formed by faulting. These are all fault lines marking the edge of it, and then faults going every which way at the extreme left end. And the relevance to water here is clear if you look at the topography superimposed on it, because as you go from the western to the eastern edge of Valles Marineris, the colors represent the topography, by the way. Red is higher, blue is lower. As you go from west to east, the geology changes from tectonics to water. All of this stuff over here are water carved channels. You can see some of the streamline shaped islands. And if you remember the flood channel I showed earlier, this is it up here on the top. And we seem to have a connection between faulting and water. The water appears to have come from beneath the surface and then flowed out over the surface. Let me draw your attention to these two again, because I'm going to make a point. And that is, if you look at this flood feature near the top and these flood features near the bottom, and look to where they flowed, those flood features are where these arrows are. And the water flowed into the northern lowlands, where it probably ponded up and created at least a short-lived ocean. Whether it was long-lived or not is debatable. There's a lot of ongoing discussion within the community, but it's possible that the water stayed liquid for a while. It may have frozen in place, and it may still be there today. What we see then is a planet in which early on there was a lot of water-related processes going on, and then it stopped. We infer that early Mars was warmer and wetter than present-day Mars. And one of the questions we're asking about the history of the climate is, why did it change? Where did the CO2 that would have produced greenhouse warming go? Where did all that water go? And there are two possible answers. The water can go down into the crust. The CO2 can form carbonate minerals. And this is a photograph of a thin section in that Allen Hills meteorite that I mentioned at the beginning. These are carbonate deposits inside of the rock. And it appears that it was carried there from the atmosphere and deposited by liquid water. Water can go down and form hydrated minerals. It may even be present in the crust today. Or the CO2 and the water can go up to the top of the atmosphere, where they can be lost to space, stripped away by the sun and by the solar wind. And this image on the right is a compilation of a year's worth of MAVEN data showing where showing how oxygen ions are being stripped away from the planet. The arrows show the direction of motion, and you can see these atoms being carried up and out and then down the tail and escaping to space. The MAVEN mission, which I was running, was geared toward understanding what was that role of loss to space. And in a sentence, the conclusion is it played a major role in the changing climate. So when you look at it all, this is the same image I showed earlier, but now the conclusion is that Mars appears to meet or to have met at some time in the past all of the requirements necessary for liquid water. And it begs the question, excuse me, it's getting late. Mars meets or has met in the past all of the environmental requirements that we think are necessary to support an origin of life or the continued existence of life. And that begs the question of, was there ever life on Mars? And if there is, could there still be some locked away in some refugia today? So I want to switch directions now and talk about how we are searching and how we have searched for life on Mars. In the 1970s, which is where I got my start in Mars exploration, we sent the Viking spacecraft to Mars. It had 2 landers that looked like this, and each one of them had very sophisticated tools to look for evidence for life. Now, we didn't send Carl Sagan along with it, although some people would have liked to, but he was able to pose with this out in the desert before it was shipped off to Mars. Viking had 3 different experiments designed to look for evidence of biology. And I'm not going to go into the details, but they each one explored a different mechanism for how metabolism could occur and how life might react. They all involved providing nutrients and carbon dioxide and water and seeing what happened. 2 of the experiments, well, first, all 3 experiments were positive initially, but they did a control experiment where they heated the dirt up first to kill off any organisms. And 2 of them continued to show that positive response, which suggests it was chemistry, not biology. The 3rd one, the one in the middle here, what's called the labeled release experiment, seemed to show evidence for the presence of life. The problem was we also sent a mass spectrometer on the left here that was designed to look for organic molecules, and it didn't find any. So if that positive response from the labeled release experiment was life, we would have expected to find organics, and we didn't find them. Now, you may have heard we did find organics with the SAM instrument, which is a more sophisticated version of the same thing on the Curiosity rover. But the organics that it found were very trace in abundance and not what you would expect to find if you are seeing evidence for life. So from Viking, what's the bottom line? I have to think, having looked at this a considerable amount, that ultimately the experiments on Viking were ill-conceived. We didn't know enough about life to know how to look for it. And as an example of that, you know, if we try to culture microbes in the lab here on Earth, go out and collect them in nature and bring them into the lab and grow them, we can only culture like 1 in 1,000 organisms. The others, we're just not providing what it needs. We don't know what it really needs in order to live. Yet we thought we could go to Mars and culture those organisms from a completely different environment. I think ultimately the Viking experiments provide us with no information. That doesn't mean that we think there's no life. It means that we think that this was not an experiment that would have shown it to us if it was there. The second search for life on Mars was with meteorites that come from Mars. And this picture on the right of the Allen Hills meteorite, I showed the same image earlier. It has evidence in it for possible life. They collect these meteorites now in Antarctica. They go down on the ice sheets in the summer. It doesn't look like summer, but believe me, it is. And if you find a rock sitting on the surface, it must have fallen out of the sky. And most of the meteorites in our collection now were collected from Antarctica. Unfortunately, nobody took a picture of this rock, Allen Hills 84001. It was collected from the Allen Hills region in the 1984 expedition, and happened to be the first rock they picked up that season. Nobody took a picture of it as it was being collected, but I put in a picture here of a different one being collected so you could see how it was being done. Why do we think these meteorites are from Mars? And there are three lines of evidence here. This is an important point. The first is, if you look at the composition of oxygen, it says these rocks are not from the Earth. On Earth, this is basically a plot that shows the ratio of oxygen 17 to 16 versus 18 to 16, three different isotopes. Every rock on Earth and on the moon falls along this straight line. I'm having trouble tracing it with my laser pointer, but everything falls on that line. The Mars rocks fall on a line that is distinctly offset from it. You can see it up here a little bit closer up. It's not offset by much, but it's offset by enough that you can't get there from here. So these rocks are not from the Earth or the moon. The age of the rocks in the middle here, some of them are very young. Within the last billion years, they're volcanic rocks. The fact that they are so young requires that they came from a planet that is big enough to have been volcanically active recently. And since we've ruled out Earth and the moon, that leaves Venus and Mars. And it's a lot easier to get here from Mars than from Venus. The real kicker, though, is in the right figure. This shows the abundance of different gases in the Mars atmosphere on the left axis and in one of these rocks on the right axis. And the gas composition is identical. To the ability to measure it, it's identical to the composition of the Mars atmosphere and different from any other source of gas we know about in the solar system. What that means is the gas must have been implanted into the rock by the impact that ejected it into space. Either these rocks came from Mars or we don't really understand anything about our solar system. I'm sorry we're not meeting in person because I would love to pass this piece of Mars around. This is one of the meteorites. You can buy them from a meteorite dealer. And I did that around 30 years ago when I became convinced that these were Martian rocks. This rock, it's about a little over 1/4 of an inch across. It's a volcanic gabbroic basalt, technically, and it looks like an Earth rock, but it's from Mars. And again, I'm sorry I can't pass it around because I think it is just so cool to be holding in your hand a rock that you know came from the planet Mars. You can go online and find dealers and buy them. And in fact, you can even buy jewelry that incorporates it. This is one example. This is an engagement ring that is being sold for more than $20,000. And it has a 10 carat, that is a 2 gram piece of Mars in the middle, and it's surrounded by diamonds there. I'll tell you though, as cool as I think this is, if I had come home to my then girlfriend and said, I'm giving you an engagement ring with a 10 carat rock in it, and then showed her this, I think I would not be married today. The evidence that people point to in this rock are things like this feature, which looks very reminiscent of a fossil organism on the Earth, a fossil microbe, and these things, which are very reminiscent of fossil microbes. Unfortunately, subsequent analysis has demonstrated that these are artifacts of the processing of the rock in order to put it under the electron microscope. There's some other lines of evidence that I won't go into, but again here, what's the bottom line? For as much discussion as these rocks have raised and the possibility that there could be evidence for life, there's nothing in here that suggests there's life. Now, there are features in the rock that tell us that water has flowed through the rock, and that's very similar to what we see in terrestrial rocks. So there could be life in this environment, but we haven't seen evidence for it yet. So what's the future now of looking for life on Mars? The next opportunity, maybe, is the ExoMars rover being launched by the European Space Agency. It's going to search for present day life. It's going to drill down to 2 meters below the surface where any organisms would be protected from cosmic rays and high energy particles from the sun and solar UV. However, this was a joint mission with Russia, and ESA has now withdrawn from that joint mission. Well, what they did was they threw Russia off, and they are looking for somebody to provide the components that Russia had provided. If they are ever able to fly it, it will be late in this decade because they have to build a lot of hardware, including the landing system, from scratch. It's not clear it will ever fly. The other way we're going to search for life on Mars is by bringing pieces of Mars back to Earth to study, by going to places where we think life might have existed, like where there was water, and bringing up rocks that may have, picking up rocks that may have some remnant, some evidence for whether there could have been life, and bringing them back to Earth. Now we're doing that today with the Perseverance rover. One of its functions is to look for samples and to collect them. Once we do that, we're going to send another spacecraft there to pick them up, launch them back into space, and bring them back to Earth. We're in the process now of developing the spacecraft that will follow on and collect the samples and bring them back. The Perseverance rover has gone to one of these, the site of one of these ancient lakes. It's Jezero crater. You can see the round crater shape here. You can see the place where water flowed into the crater. You can see over on the other side where water flowed out. And if we look close up at where the water came in, we can see this delta that formed where the water coming in flowed into a lake and deposited its sediment. Perseverance landed over here. I believe right now it is somewhere over here. It has been collecting samples from the delta and from the region of the lake beds, and it's moving upstream to where there may have been more standing water. You know, other than sample return, there's still a lot of science we can do at Mars. And this is a summary from a recent report that I shared looking at what the science is. And there's no dearth of important science looking at the nature of habitability and potential for life, what drives planetary climate change, how planets evolve, what drives a planet, using Mars as an example to understand planets around other stars. And then finally, thinking of Mars as a destination for human exploration and a place that we may send people within our lifetimes. These are important science questions. Some of them will be addressed by Mars sample return, and many of them will not. So we're working now to try to develop a program of Mars exploration that would run in parallel with this sample return effort. Well, let me go a little bit farther into the future and talk about human missions to Mars. I think this has been one of the goals of NASA's Mars program since the 1960s. And we're getting to the point where we might be able to do it. This is Elon Musk's version of what a human mission to Mars might look like, with his Starship delivering people and supplies to bases on the surface. I read just the other day that he's talking about putting 1 million people on Mars by 2050. We can have a long discussion of whether that's feasible or not. And maybe if you fax me that beer, I'll tell you my thoughts on it. I think more realistic is a first human mission to Mars. Remember that with all the grand plans that Elon Musk has, we haven't sent a person to Mars yet. I have a picture here of Lockheed Martin's concept for a Mars mission. This is an orbiter, either a flyby or an orbiter, and you would separately have to send a lander. It's feasible. We can actually carry out a human Mars mission within the next 1 to 2 decades if we have the will. And the will means the willingness to allow people to take the risk and the willingness to pay for the cost, because this would not be cheap. We can look farther into the future at whether Mars can be terraformed. You know, Mars once had a climate like the one in the lower right, well, maybe except for that green stuff, but it once had a climate where there was liquid water abundant and maybe flowing over the surface, maybe present as an ocean. Mars dried up. Is there anything we can do to change the climate back? Can we put a greenhouse gas into the atmosphere and warm it up enough that liquid water would be stable, that people could walk around without spacesuits? And I do have a quote from Elon Musk on this. You would need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on. And I think he's referring to without having to have a spacesuit on, rather than thinking of Mars as one large nudist colony. But with Elon, you can never quite tell. He did describe it as a fixer-upper of a planet. Can you terraform Mars? Is it possible to change the climate? We know that Elon is serious about doing this because he has a slogan, Nuke Mars, which is how he thinks we can do it, and a t-shirt. And if you have a slogan and a t-shirt, it must be real. But let's evaluate this from a scientific perspective. Where could we get enough CO2 to put into the atmosphere in order to terraform Mars? We can get it from the polar caps. We know that there's some CO2 in the polar ice. It would maybe double the atmospheric pressure. It's in the ground. Each molecule grabs onto a dust grain in a process called adsorption. We know that there are carbon and CO2 bearing minerals, carbonates, and if you heat those up, you can get the CO2 back out of them. However, a lot of the gas has been lost to space. We can also wait for continued volcanic outgassing to replenish the atmosphere. Does this make sense? Is it feasible? Unfortunately, the amount of CO2 that is there is very small because most of it has been lost to space. And that which is still there is very hard to mobilize and put into the atmosphere. So can Mars be terraformed? I think the answer is no. We cannot do it with materials that are indigenous to Mars. That is, with water and CO2 as greenhouse gases. Don't give up hope entirely, though, because one can always envision the possibility of manufacturing what I'll call boutique greenhouse gases, things like chlorofluorocarbons, but even more effective than that, and putting them into the atmosphere and warming up the planet. That might be feasible. However, keep in mind that the type of manufacturing capability we would need in order to do that would be tremendous. And we haven't even sent a person there. Plus, there's a danger in thinking that we can terraform Mars and, as Elon Musk describes, use it as a backup planet. If we think that we have a backup planet to go to, we're not going to take good care of the Earth. That's expressed in this Calvin and Hobbes cartoon that I particularly like. We need to take care of the Earth. However bad the climate on Earth ever gets, whatever we do to it, whatever nature does to it, it's going to be easier to fix that than to change the climate on Mars and make it more Earth-like. We're only this far away from the ideal climate on Earth, And we're this far away from having a viable climate on Mars. This is my last chart, and I was trying to think of how to end this with something pithy. And I've given up, but I did write down, we've only just begun to explore Mars. And what I mean by that is Mars has a lot to tell us about how planets work. It has a lot to tell us about not only planets in our solar system, but planets orbiting other stars. Mars is the closest planet where we can send people in order to continue that scientific exploration. And it's the closest planet that has the possibility of having life present today or having had it there in the past. And I think that a discovery of life that was independent of terrestrial life would truly go down as one of the most profound discoveries in history. So I think Mars is the place to be. It's the place to go. And as somebody said at the beginning, our children, our grandchildren may be able to explore Mars. I just hope they can come back. So thank you very much. I appreciate the opportunity to meet with you and talk with you. And let me stop sharing here. And I'm happy to answer questions or have a discussion as you would see fit. Thank you.
Thank you, Bruce. This was very, very informative and very appropriate for us to understand. There are some questions. I see Ron is raising the issue of lack of magnetic field around Mars, whether that further complicates the terraforming the planet.
Well, I'm not convinced that we need to further complicate it. I think that the question of finding a gas to warm it up is complex enough. But I think you're right. The presence of an atmosphere, the history of an atmosphere is intimately connected to whether there's a magnetic field. One of the things that Maven was exploring in the loss of the atmosphere to space was what role does the magnetic field play? Mars doesn't have a magnetic field today. It did in its earliest history. And we think that the turn off of the magnetic field about 4 billion years ago was what allowed the turn on of stripping of the atmosphere by the solar wind. Today, Mars doesn't have a magnetic field, but the other thing that has changed is that the solar ultraviolet light and the solar wind have diminished incredibly since that earliest history. So all the action of the sun stripping gas from the planet occurred early in that first billion years. Today, the rate of loss of gas is maybe 2 or 3 kilograms per second, which is not terribly significant. It does let us understand the processes. If we could somehow, let's see, what am I trying to say now? I'm trying to say that if we could put gas in the atmosphere, it's probably pretty safe, that the sun is not intense enough to strip it away very quickly. If we wanted to be on the safe side, one scientist has proposed creating a giant electromagnet and putting it upstream between Mars and the sun so that it would generate a magnetic field, stand off the solar wind and keep it from hitting the planet. I don't think that's necessary.
You didn't mention anything about the 2 moons that Mars has. Could they play any role in any of the explorations?
There's a lot of talk about that. In fact, the Japanese Space Agency is currently developing a mission to go and bring back samples of the surface of one of those 2 moons. They're very small moons, very, very different from ours, 10 or 20 kilometers across, whereas ours is what, 1,800 kilometers across radius, I think. And understanding them is important for understanding the evolution of the Mars system. Why are they there? Are they captured asteroids? Did they form in orbit around Mars? And that may tell us something about what the early dynamical environment was like. It's a lot easier to get to the moons of Mars than to get to the surface of Mars. So that is one reason why they might be an exploration target. Plus, I talked about meteorites that are collected on Earth that come from Mars. They get knocked off by asteroids and ejected into space and eventually end up here on Earth. A lot of those would end up on one of the Martian moons. So you could actually collect a tremendous diversity of rocks by going to the moon and picking up samples and bringing them back.
Okay. Any questions? You can raise your hand and I can recognize you. Any questions from the audience? Yes, Dina.
So my question is about the idea of sending people to Mars. The idea that the first batch of people who would go to Mars would not be able to come back. Is this something that's really being considered?
It depends on who you ask. I think it's a horrible thing to think about sending someone on a one-way trip to Mars.
I do too.
Mind you, there are people I can list who I would want to send on a one-way trip to Mars, but that's a different story. I think that, when we send astronauts into space, we do so with safety as the highest criterion. We risk lives, but not unduly.
Right.
People die in astronauts have died. But we do everything possible to bring them back safely.
Yeah.
The type of person that would want to go on a one-way trip, I would worry about sending them.
Exactly. Yes.
Now, and the first human missions to Mars are going to be in vehicles the size of a Winnebago. And I can't imagine, even if that worked, wanting to spend the rest of my life sitting in a trailer not doing anything.
Right. Yeah. Okay.
I think we have to work under the assumption that it's a round trip and we're going to do everything to make that happen as a round trip. And if we can't have high assurance that it'll be successful, we're not ready to go.
Okay, good.
Let me say it differently. It's if once you get people there, the additional effort to get them back is not that great. The hardest part is getting them there in the first place.
Okay.
And making them survive till they can return.
That's right.
Yeah. Good.
We have Christopher
Wyland.
Yes, hello. Good evening. Bruce, thank you for the presentation. First of all, it was awesome. I really appreciate it. I was fortunate enough, my spouse is a Boulder graduate, so I actually got to watch Maven launch, which was an absolute, I'll never forget it. Fantastic. If anyone gets a chance to do that.
Thank you. I won't forget it either. It was a singular event. I will say my wife was out on the causeway with 200 of our friends and family. And I'm told she was just totally beside herself going, my God, how are we going to console them at our party tonight when the thing blows up?
I never thought for a second it would blow up.
I knew the odds, unfortunately. This is the business we've chosen.
Yeah. Well, so Bruce, I do have a question for you. The idea of astronauts are very sexy, right? We've all seen the movies, we've all heard the stories told, but automation and robotics have leapfrogged what anybody thought we could do probably 20 years ago. Could you talk about any particular science that you and the folks you're looking at consider that make it necessary for the complexity and the very cautious fashion you have to do to basically keep a human being alive that would be more important than sending robots?
I'm glad you asked that question. This has been a very visible question in the media this past couple of months. There was a recent book, maybe a month ago, that came out by Donald Goldsmith and Martin Rees, called something like The End of Astronauts, asking that exact question, and for the exact reason you mentioned. And their basic point was capabilities are growing so quickly that pretty soon robotic spacecraft will be able to do everything that humans could do, and more safely, more cheaply. The answer that I would give is we're not there yet. Even they admit that we're talking decades into the future before we have the capability really equivalent to humans. And as far as I'm concerned, when you're talking decades into the future, you're into some unknown time, 25 years, 50, 100, you don't know when that's going to happen. I think that today and for the foreseeable future, humans have the capability that robots don't have. And I'll give you two examples. One was with the Apollo missions on the moon. The astronauts were able to observe things and use intelligent sample collection. And one of the things they observed, they were walking around and they go, my God, that dust over there is orange. And they saw it in a way that would not have been seeable by a robotic spacecraft. And it turned out to be a very scientifically important, geologically important volcanic material from fire fountaining. Now, admittedly, that's 50 years ago and technology has changed, but the point is the same, that humans have capabilities that robots don't have. The second example I'll give is with the Spirit and Opportunity rovers. Opportunity operated, I think, for 9 years. And the principal investigator of that mission, Steve Squires, was asked at one point how long it would have taken a human to do what the Opportunity rover did. And what the Opportunity rover did in a year, a human on the surface could have done in an afternoon. It's incredibly valuable science robotically, but it's not what humans can do. I think that there's always going to be a capability that humans have. We've got the best remote sensing devices in existence in our eyes, and an incredibly complex, sophisticated computer in our brains, and they're coupled together. I think humans are always going to have capabilities that robotic spacecraft won't have. And if I'm wrong, it'll still be several decades before that changes.
One question I have, Bruce, is there are several countries now having Mars missions, and recently UAE even had a, I think, orbiter around Mars. What is the international collaboration between all of this? How is that achieved?
Let me first tell you that I'm also a science investigator on that mission from the United Arab Emirates. So I'm participating in that. There's collaboration at multiple levels. I mentioned with the ExoMars rover, the collaboration between the European Space Agency and Russia. By the way, that was initially a collaboration between ESA and the US until the US backed out. We've collaborated on building joint spacecraft like the Cassini spacecraft or the Galileo spacecraft, or a Jupiter orbiter with probe. So we do things jointly like that. We're moving toward joint programs involving hardware for the human missions going back to the moon. In addition, The easiest collaboration is to share data. You know, I was the principal investigator of MAVEN. The MAVEN team just reached an agreement with the Emirates Mars mission team from the UAE on collaboration and data sharing, because the science doesn't care what country anybody is from. People from Asia are using the MAVEN data. People from the US are starting to use the Emirates data. There's a lot of opportunity for collaboration. And as we get into more and more complex, expensive missions, there's the opportunity to offset some of the cost by having it shared among multiple countries.
Good, good, thank you.
Christopher, I think you had unmuted and we're going to follow up on your question from a minute ago.
No, I didn't, Bruce. I just wanted to thank you for all that you did. Maven has been a joy for us. Thank you.
Thank you. And thanks for those nice words about having been to the launch. I agree. If you ever have the opportunity, please go. It is worth seeing one in person.
Most certainly.
Okay. Well, I don't see any more questions. So thank you very much, Bruce. We very much appreciate your presentation, and it was very informative, and really appreciate your putting it together and delivering it. Thank you very much.
Thank you. And thank you for the opportunity to talk with you. I really appreciate that. I'm always glad to talk with people who are interested in exploration of Mars.
Okay.
All right.
Thank you.
Thank you very much.
I know you have more business tonight, but I'm going to sign off if that's okay.
Yes, that's all right. And have a good evening.
Thank you.